organizing for the afternoon session. We are going to have some more, exactly 1, 2, 3, 4, 5, 6, 6 or 7.
The communication is very bad. The connection was very bad while you were talking.
Now for me it's perfect. I don't know on your side, but on my side it works fine.
So there is one of my colleagues here, Paolo Francavilla.
Hi, pleased to meet you. So I was only somehow cheering up the audience with what will actually happen in the afternoon. After your talk, there will be 6 more short talks by colleagues Marco Di Natale, Santana, Nicola Tonellotto, ISTI CNR, Andrea Mina e Arianna Martinelli Sant'Anna, Ercan Kuruoglu ISTI CNR, Alessandra Righi from ISTAT, and Pierluigi Lopalco from University of Pisa Epidemiology. So we have another quite interesting array of presentations. And after that, it will be the first 4 students of the first cycle of the PhD presenting their current state of affairs in their own thesis. The other 4 will be for tomorrow afternoon. Okay, this is the plan of the afternoon session. I think whenever you like, we can start with your presentation, Chiara.
Okay, so before putting up the slides, I have to greet everybody. I'm sorry that we are here at CERN and not in person there, because it's usually more difficult to follow. But I'll try to do my best. So I put up the slide now, the sharing, the script. Okay, so the idea is to give just a very short peel on what would be a thesis in this field, where we practically study the structure of matter in the elementary state, when we go really to the elementary constituents. So this kind of research is done at the University of Pisa, but also in connection with the INFN, which is the Institute to Study Nuclear Physics. And last year we made 3 examples of studies that were using advanced technique of analysis. And here you have the 3 boxes that we also showed last year. One in particle physics on the left, and then gravitational physics in the center, and medical physics on the right. So for the medical physics, in fact, you have 2 students, one of in 2 different years, that are applying data analysis technique to magnetic resonance images to study structure in the brain. So, but today I will concentrate in one example in particle physics. So, particle physics is the whole branch of physics that explains how matter interacts at the elementary level, and in particular, for example, explain how the sun works, how the nuclear reactor works, why the atom is done the way it is done. So now, where do we get data to understand the structure of matter? So what we do, practically, we obtain images, particles, constituents of matter, by smashing protons at very high velocity in laboratories. So CERN, where I am now, is one of these laboratories. In fact, it's the laboratory where we have the machine to accelerate protons at the highest energy that we can obtain in laboratories. So now, just to give you some idea of what we mean by smashing proton and what we get out from the smashing of proton, I'll show you a small movie. This is the real accelerator. So the accelerator is underground, about 100 meters, and it's 24 meters in circumference. And now here is a cartoon. You go inside the accelerator, and that was the proton. So the two protons reaches one from one side and the other one from the other one, and you see this cylinder is the place where the two protons collide, creating hundreds of particles that cross our detector, giving us an image of the creation of these particles. Imagine that the detector is made of many different kinds of technology, but just to give you an idea of the quantity of information that you get, is composed by about 1,000 million of channels. So each time we see a picture, we look at the signal of 100 million channels. So this picture of the particle produced from the smashing of protons is what we call the event. And from there, this is our data. And in fact, when each single image is not very big, because we throw away all the channels that do not have any signal, and we have about 1 megabyte per image, which is the size of the picture that you take with your phone, more or less. But the problem is that we produce 40 million images per second. And so we save only the events that we believe are interesting, which is about 100 images per second, producing something like 50, 100 petabytes per year. Now, here on this image with balls, I want to compare the quantity of data that is produced in LHC with respect to, for example, the yellow ball is what Facebook, the data that is generated in Facebook with flows. So in 1 year, Facebook see about 180 petabytes per year, and the light yellow and the light blue is the data produced in LHC. So you see that it's very comparable. So in fact, this is really a factory for big data, and this is one of our problems. Managing this huge amount of data and being able to extract from this the information that is interesting. So on this slide, I explain practically what we do. In the yellow box, I say our job is identify interesting events which are rare among a number of common events and measure a characteristic. So the interesting event is what we call signal, and the common event is what we call background. So I make one single example, which is also related to the analysis that we make in our group. So the example that I want to make is the search and identification of Higgs particle, which is the last particle that has been discovered. You may remember a few years ago it was finally discovered here with LHC, and now we are studying them. So the problem is that these Higgs particles are very rare. So we create smashing particles about 1 Higgs per 1 meter of events which are background. So what we need to do is to develop an analysis which is able to recognize these few events from the huge background. So what we do, we use at the moment, so we started with very simple analysis, but at the moment we use a multivariate analysis. In fact, what we do is we use a boosted decision tree, and this is the idea, which I will show in the next slide, is that we can use many different characteristics of the event, like energy of particles, direction of particles, and other things, and we can put all together and use this boosted decision tree to give us back a single variable which is able to detect identified background for signal. So here I have also put a link to this package, which is an analysis package, which is used very much in high energy, and you can have a look at what it is. So just a few slides to give you the idea in a very, very simple way, naive way, why the boosted decision tree is nicer than just cutting on single variable. So now here I have two variables as an example, and what one could do. I mean, we have in red the background and in blue the signal, and you see that this variable gives a bit of separation between signal and background. So what I could do is I could select only those events, for example, that lie in the region that I show with the green arrow, and just to select those areas. But if you look at the correlation, you see that the distribution again, this is shown in a scatter plot where the two variables are shown together, and you see that they are very correlated. And so the simple cut with the green line would not do the best selection. The best selection would be to do something like this, so to really separate with this green alpha circle. And this is exactly what the boosted decision tree does for us. So you see that using this boosted decision tree algorithm, I show the output here on green, on red we have the background, in blue we have the signal, and now they are very much better separated. And this is what the boosted decision tree has done, has constructed the black line to separate the two samples. And this is my last plot. I want to show you what the reality. This is blue data. I just spend a bit of time to explain what we see. So on the x-axis we have the real decision tree, which contains tens of variables, and the more you are on the right, the more you see the signal, the more you are on the left, the more you see the background. So the small red histograms is the contribution of signal, while the other color show you different type of process which we consider background. And finally, what is very nice is in black, the full circle. This is the data, which you see very well we can predict. Okay, so what is the next step? This is what we have already done. So I go to my thesis proposal. What my proposal is that we could improve the sensitivity to search in the X and to select X events using more advanced classification. And there is already the possibility with the software for the analysis to use Keras or TensorFlow framework to implement the actual network, which can be many different types, deep neural network, adversarial, and systematic aware, and so on. Why it would be very interesting to do a thesis in physics, let's say, but within the data science. I think because it would be a unique opportunity to have experts from these different disciplines in a common place, and really it would be much easier to do a step forward, putting together different competencies. Moreover, clearly there would be the possibility to spend time in CERN to interact with the rest of the collaboration. So now I'm giving this very simple example, which we would be interested as a group because we work on this, but I want to give you an idea of how much this the activity of machine learning is going on in our field. So this is the program of the third Atlas Machine Learning Workshop. And luckily this is private, so I didn't put a link because you're not allowed to see it. But in this last slide, instead we have the Inter-Experiment Machine Learning Workshop, and this is public, and so you could have a look at the type of studies. There are very many applied to different things in analysis and in reconstruction of the events in which machine learning is applied. Okay, this is all. Thank you for your attention.
Thank you, Chiara. Very, very clear and I think very well put. I'm not sure we will have time for question now because we have a very, very packed program. But I think it's the message is very clear. I think, and I totally agree that the physics of matter is certainly a very interesting field for a challenging field for machine learning tools, and also for not only for finding better models, but finding better way to explain the sense of the discovery, right? Because this is part of scientific discovery.
So listen, if you can distribute the slide, and then there is also my contact, and we are happy also to answer mails and give information to anybody.
Okay, thanks a lot. If you can share the slides, we will post it on the website of the event so that people can only have a chance to look at them offline. Okay?
Okay. Ciao.
Ciao.
Everybody.
Thank you so much. Bye bye. Molto bene. Let's. Sorry. Sometimes we proceed with Marco Di Natale. Santana. Marco is about autonomous driving and more. So another very challenging and very interesting application field for data science, machine learning, big data, and so on. Because this particular kind of robots are going to change our life very shortly, right? Possibly.
Maybe or maybe not. We'll see. Okay, well, first a very, very short introduction. Thank God it's only 15 minutes, because I'm afraid that whatever I'm going to say is going to be very light for most of you. Can you hear me?
No.
I prefer to shout.
For the stream.
Oh, it's for
Because the people are not streaming.
Okay. Sorry. Okay, so it could be very boring for some of you, and it's very, very high levels. On the other hand, it's only 15 minutes, so bear with me. Won't be too hard. What I've been asked is, can you explain what are you doing in your lab and what are the connections with the general framework of big data? So this is more or less the picture. But first, before I go into the application, we are one of the institutes of the Scuola Superiore Sant'Anna on the general field of engineering, which is computer engineering and telecommunications. And in our lab, we're dealing specifically with embedded systems, and we are more or less 30-35 people. So we have a number, as many other labs here, cooperations with other universities in Europe, the US, and a lot of companies, because I mean, these things, this is the first part of the message. Embedded systems are very, very hot these days. It's a market that's been slowly growing. We didn't have the dot-com boom, the internet boom of 15 years ago, but it's been ever growing. And it's much easier to see on the other side. You probably don't realize you're all too young for this. But people of my age, we used to have a market dominated by German manufacturers for cameras and scales. And those are no more there. And the reason why those are no more there is that because they refuse to put electronics into their equipment. So embedded systems is about putting electronics, computer, logic, functionality into your typical mechanical device or your everyday, well, a car is an everyday device, right? But it's also in your oven, it's in your washing machine, it's everywhere. If you count how many computers you have, meaning CPUs, microcontroller, you most likely have 5 or 6 in your cell phone. When you're driving a car, you probably don't realize, but you have tens of them, or even more. So we're actually surrounded by these computers that are controlling small aspects of our everyday life, and especially the automotive domain. An automotive system these days, it's more complex than an airplane, okay, in terms of numbers of lines of code. And again, we're going towards hundreds of CPUs inside the car. Now, what are these CPUs doing? Well, before we get there, why can we afford to have so many of them? Well, we can afford to have so many of them because the price, if you do the math, the price for a microcontroller now is below $1. And as a matter of fact, you can go on the internet and buy things like this, in which you have small devices for less than 100 euros that are already multi-cores. You have 16 cores, 16 computers on a single board that is less than 100 euros. So the message here is computers don't cost anymore. Getting the equipment is easy. You can get hundreds of cores relatively easy these days. Getting the computing hardware is not a problem. The problem is what you program on top of these things. And one very hot application these days, a lot of companies have jumped into this, and Google is one of them, is autonomous driving. Now, I just wanted to give you a feeling about what it means to build an autonomous driving car and why this is related with big data. Now, you see the device that's on top of that. Even if some models these days are trying to get rid of this, this is called LiDAR. Okay, this is a radar that's using light, okay? And a LiDAR is going to produce a map. This is a reconstructed image made of dots. And every dot that you see there has been recorded by a LiDAR. So a LiDAR is continuously scanning the environment, getting an image of the environment three-dimensional with a resolution in the order of 1 centimeter from a fraction of a meter down to 200 meters. So you can imagine how much data you need to process for each and every revolution of this thing that is, by the way, rapidly spinning. It's a huge volume of data. And out of this huge volume, you need to detect all the elements of interest for your car. You need to detect the road plane, the road markings, all the, well, traffic lights, whatever is going to affect your driving. You need to merge this with GPS data. You need to detect other vehicles. You need to detect the pedestrians. And once you do this detection, then you need to perform the logic, the intelligence about driving, which is not simply get the best path on a given road that you detected, but it's also interacting. It has to do with other cars, it has to do with people that may cross the street and so on and so forth. Okay? And this is all happening. Let's see if I can get the, yeah, I can get the audio here. This is again a prototype. This is old, okay? This is stuff that is at the very least 5 or 6 years old. This is a demo for an autonomous driving car by Google. You see a driver there, but it's passive. Okay, this guy's not doing anything. So the thing that you see spinning on top is the LiDAR. So you can imagine how fast and how reactive this system needs to be. So now you have big data processing, which is very complex, huge amount of data. You need to do it in real time, very fast. And the last message, you need to do it predictably in such a way that you want to guarantee safety. Now, I started this talk saying, I don't know if we ever going to really use the systems in our everyday life. Because the challenge is not about having it drive. It was already done 60 years ago, okay? It's not about what happens in 99% of the cases. It is about that safety case that happens with, let's say, once every 10 to the minus 6 runs or things like this. You need to be safe to that degree. So mixing big data, handling of large quantities of data with intelligence, with real time, and especially with safety, that is going to be the big challenge. Now, again, you can change the LiDAR with multiple cameras. By the way, this car here, this is from a startup in Parma, sold 2 years ago for 30 million euros. So, just to say that these things also grow from universities, of course. And again, your cell phone with Google is sending your position data, if you allow it to do so, to Google every time. And, well, you can use this position data when you have Google Maps to have the traffic in real time. But you can also use it to basically do the reconstruction of any map. So these are the taxes in a day in San Francisco. So again, lots of data coming from your devices for multiple applications. Now, what is also very interesting, I would say probably the most important to us is also the last one, predictive maintenance. This is also something that whatever company you go and talk with, from here in Pisa there is Enel, electric energy supplier, for those that are not Italian, I guess. But again, whatever industry you're coming these days, they're interested in predictive maintenance. Now, doing predictive maintenance on some equipments that include rotational machines may imply sampling a very high speed, again, of very large quantities of data, trying to detect anomalies, probably in the frequency domain, that are the typical signature of a fault that may happen in the future. And again, this is of course, you can imagine if you can predict a fault and plan for the replacement or a part or a machinery in advance, makes a huge difference for lots of markets. Other things, smart grids, electric vehicles. I mean, only have 15 minutes, but it's easy to realize that really whenever it goes to the electrical infrastructure, it's all going to be interconnected. Several electric suppliers are already planning on using your future electric car as a battery. So you can make a contract with the energy supplier in such a way that when the energy supplier needs energy, it will get the energy back from your car. Okay? So this is just a way to say everything is going to be interconnected. In order to predict and to manage this system at best, you need a real-time evaluation and information of large quantities of data. This is it. I don't even know if I'm long or short on my slot. The final message is that actually, thanks to an initiative of the Italian Ministry of Education, we have right now funds. We bought machines with lots of cores, and our target is exactly this. Doing research on ways to have AI that is predictable. Predictable meaning predictable in time and predictable with respect to the required safety. Okay? That's more or less it. Thank you.
Thank you very much. Thank you. Yes, absolutely. One of the main challenges of modern AI is precisely to make it sensitive to context, to increase safety and to increase the usability by people in complex situations. The next topic is actually text mining. The text is not being evocated so much up to now, so now we have actually Nicola Tonellotto that is going to talk about some challenges related to the management of text in
Okay.
Nicola is from the HPC lab at ECCNR.
Okay, thank you, Dino. Welcome here. In this presentation on some works that could be done during your PhD studies, I let's say, with respect to the presentation I've seen this afternoon, sorry for not being here this morning, I take a different approach. So I want just to discuss a specific topic on which we would like to investigate in the next months, years, give you some feeling about what are the current techniques that can be used in that topic, and then give you some open questions to think about. I swear I try to reduce as much as possible the number of mathematical formulas in my slide. I have 15 slides and was happy to reach just 27 formulas lower bound. No kidding. There are just 2, but for no way, not at all mandatory to understand them if you just watch my hands like a wizard. So here we are speaking about word embeddings. Word embeddings are quite recent. Is a quite recent technology in text analysis / mining / processing, in which we get words from any set of documents and we represent them as numbers. Okay? We represent them in particular in the form of a vector. I'm not interested how these vectors are generated. There are unsupervised learning algorithms to generate such numbers. At the end of the day, we end up with vectors in a vector space. Okay? The good thing about that is that similarity among vectors is strictly correlated with similarity at the level of semantics of the word. Okay? And it is possible to have a kind of linear function that maps the analogy relationship. So, for some strange reasons, a reason that is not clear enough now, we can write down an equation like that: king minus man plus woman equal x, and passing to the representations, the answer will be quick. So, what we have on a large number of dimensions, hundreds, thousands dimensions, millions or billions of vectors clustered through semantic meaning. Okay? What do we plan to do with word embeddings? This word embedding, that is not something completely new because there are applications coming from the computer vision and image recognition fields that really use such kind of vectors. What can we do with such word embeddings when we want to deal with them in information retrieval? So the first question that naturally arises is, can we get some special structure out of those apparently random vectors in this vector space that we can leverage? Of course, yes, because already we know that similar words are clustered together. Can we imagine topically similar words that are words speaking about, I don't know, sentiments or journalism or holidays, living close enough in this multidimensional vector space? So, if we get all these vectors, basically, let's assume for now on that they are just three-dimensional points on a soccer ball. Okay? Is it possible to assume that there is some kind of clustering of this hyperbole of vectors that we can represent in unitary norm that exhibit some special structure? The answer, of course, is yes. I will show you how. And since it is possible, can we leverage this special structure to compress the vectors? It could not be so easy to understand why we needed to compress them, but follow me up to the last slide. It's one of the hot topics today. Why? Because when we think about 500 dimensions, every vector is basically 500 float numbers to be stored on a device. And we have millions of them. And we want to use them efficiently to perform searches. Okay? We can imagine a lot of applications. The most important one now is, given a vector, a word embedding, find the top key, top 10, top 20, closest vectors to the one that we give. think of a vector as representing a query submitted to a search engine. And think of word embeddings as representation of documents. The 10 blue links are basically the 10 closest vector embeddings close to the user query representation. Okay? So this is not new, it's quite a recent development about their compression. Is basically we are in this multi-dimensional vector space. I call it D. We think about the tree, the ball. Okay? So, how to compress them? The easiest compression that you can imagine is to just reduce every single dimension to a binary digit, 0 or 1. We are moving from an almost infinite number of floats to just 2 numbers, 1 bit. Is it feasible? What is the error that we introduce in doing such an approximation if it's feasible? Okay? Basically, what do? We take just the positive orthant slice of the ball where the numbers are 0 or positive. Okay? And what do? We build around this ball a cube. Our representatives in the compressed space are the points of this cube, with the exception of 0. This is the slice of the soccer ball we are considering. Okay? When we connect all those points that are represented by binary digit to the origin, we get some landmarks on the surface of our soccer ball. Okay? Easy enough. When we have a random means any kind of word embedding living on this soccer ball, we compute the closest landmark, this point, out of those simple 7 points. Okay? And this is the compressed representation of that vector. Out of a lot, just 7 of them. Why are we doing that? Of course, because representing vectors with bits is far better than representing them with floats. But can we do something interesting with this representation? The first question is, can we do something better than with original vectors? The second is, what is this, what we need to pay for such benefits? The first is searching on this space of binary vectors is amazingly fast. Okay? Even if we think that the number of dimensions is increasing and the number of possible landmarks exponentially increases with the number of dimensions, is quite easy leveraging the fact that we have at our disposal only zeros and ones to search for them. I don't want to go through the algorithm, just believe me. I will give you references at the end of the slide. Okay, but what we pay is that, of course, we have a quantization error. Okay, this quantization error, we can make a lot of lemmas, a lot of discussion. Basically, what we are doing with that, we are taking this ball and we are tessellating it, like a polyhedra that I've shown you in the original picture. What is the interesting thing of this tessellation using bits? Is that the tessellation is at a finer grain close to the center and very large grain close to the border. Okay, so we have a lot of landmarks very concentrated in the middle of our slice. So when we want to compute a compressed representation of our random vectors, what we would like to do, to put as many word embeddings as possible far away from the borders and close to the center. Okay? This is something, okay, the tessellation, the search algorithm of the factor standard. This is something rotating the vector representations in order to minimize the error is something new. And it's something very interesting because it depends on the nature of the data. we are compressing. It depends on the specific set of vectors we are considering. Okay? So, this is just a very, not actually very complex formula, stating exactly what I say. Given a random set of points on the positive orthant of our soccer ball, what we are looking for is basically the best way to rotate them in such a way to place most points close to the, far away from the borders. Okay? And this is a very difficult problem. Okay? That can be solved with solving this equation, but this is a very interesting approach. I don't know, I have 2 slides, yeah. Of course, stemming from that, we can say, what about vectors that are not just positive, that we have negative and positive components? Okay, no problem. We move from the single slice to the whole ball in D dimension, and we get far more discretization points. Okay, I hope that I attracted the interest of some of you. But what we can do with that? Okay, why are we discussing this? Because it's very interesting what we can do next with those approaches. Okay, first question is, what about, instead of preserving, everything is done in order to preserve the angles between vectors. But in many tasks, we are not interested with the angles, just with the relative order. I don't want to know that between the first and the second point there are 3.5 millimeters. I want just to know which one is the first, which one is the second, which one is the third. I'm interested in ordering. That's it. So is it possible to structure this need in order to leverage more compression? And different research questions stated here are still under investigation. And I'm close to finish. The next one is...
2 more minutes.
Yeah, is far more interesting and up to date. I guess that you had a lot of presentations speaking about the neural networks, deep learning, stuff like that. Okay? Can we leverage this technology, this approach, these algorithms, in terms of neural networks? Believe me or not, in the next decade, the neural networks, shallow or deep, will start moving away from the clusters of GPUs in the data centers of research agencies and big companies. Okay? They will be trained and deployed on resource-constrained device, on your mobiles. Why? Just think about the GDPR. The data will not be that you have about your behavior will not be allowed to be moved in a data center. So it will be necessary to find ways to train, store, that is, compress and efficiently manage this information on a resource-constrained device. This opens the door to a new world of research questions. And the main one is an approach similar to the previous one is feasible when we think about the rows or the columns of the vector of the matrix between the layers of any kind of neural network. Still have no answer. Okay? And I conclude, I don't know if the slides will be distributed, but if you want, if you are interested and you want some references, here are the mathematical blah blah about all the content. As you can see, quite recent, and the middle one is Google, and there is an open source project released by Facebook and used actually by Facebook PICE, that is an implementation of the main state-of-the-art techniques to do exactly efficient, I always have a problem, nearest neighbor search on word embeddings. Please check the code if you are interested, clone it and test it. billions of word embeddings are just ready for you to download and test on this platform. I'm not part of Facebook, I'm not a researcher there, I'm not disclosing any information or make advertisements, okay? Thank you.
Thank you, Nicola. Yes, the slides will be distributed. So if you send them to us, we will make them available on the website. And we can proceed to the next presentation, please. So Andrea Mina and Arianna Martinelli from Scuola Santana, they were talking about technological knowledge, firm growth, and industry evolution. So a presentation in the spirit of management and innovation. Manufacturing.
Okay. Good afternoon. I'm Andrea Mina. This is my colleague Arianna Martinelli. A bit of economics for the afternoon to cheer you up. We are both at the Scuola Superiore Sant'Anna. We actually started working on very similar topics in different lands. I worked on the Brexit-affected shores of the UK, in Manchester and later in Cambridge, and Arianna was on more solid land in the Netherlands and then in Italy. We took very similar approaches to economics in general, so I just thought that before introducing the topic on which we thought that there might be some overlaps with interests some of you may have, let me just include one slide about a particular way of treating economics as an evolutionary science, and a particular approach that stresses the coevolution of knowledge and competencies and economic structures. It's not obvious because the still dominant approach in econ is an equilibrium approach, and then there are some alternative schools, some stress more the institutional aspects, and one effectively says, well, you know what, dynamics first, so let's treat the economy as a set of dynamic processes, and let's really look into what knowledge is and what technologies are. And there's actually more and more information about it. The focal questions are, what's the rate of technical change? What's its direction? Okay? Can we observe patterns in the overall evolution of technology? What do they depend on? Do we find bifurcations? Why? Do we find convergence? Do we find parallel developments? Why? When? And there's quite a lot of theory and empirical evidence that has accumulated over time. I'll leave the mic to Arianna to lead us through the treatment of technology space and, as you'll see, technological trajectories, and there's quite a lot of work in Pisa on this particular topic.
Thank you very much, Andrea. So, well, a useful way to think about the evolution of technology is to use the concept of technological space, and this can be defined as a real topological space in which innovations, or more broadly speaking, like a solution to technical problems, are distributed. And actually, of course, are not evenly distributed around the space. And the agents, that could be, let's say, inventors or engineers, actually explore this technological space, and so they find new solutions, and basically they find new innovations. And the reconstruction of how and the extent to which the technological space is actually explored is very informative about the type of the dynamics of the resulting innovation process. For instance, if an agent tends to search very close around in the sort of known neighborhoods, we could expect that the innovation resulting from this process is more cumulative, more incremental, which can be desirable, but of course offer, let's say, less level of opportunities. On the contrary, when you try to go to really uncharted territories, there might be more opportunities in terms of originality. You might find even technological breakthrough, but you are in uncharted territories with a high uncertainty, and so probably, and therefore more likelihood failure. So this technological space is quite important in trying to explain how new innovation emerges. And of course, this space is not infinite, and there is something that is binding this technological space and the way also the agents, let's say the engineers, search it. And this is what Giovanni Dosi, in a quite important paper in 1982, called a technological paradigm. So basically, these technological paradigms define within a technology what are the main technological bottlenecks tackled by the engineers, what are the heuristics that engineers tend to use in order to address these technical issues, and also the technological competencies, so the science and the technical aspects that are needed within a certain technology. And within this broad technological space, bounded by the technological paradigms, we can still observe like local and cumulative patterns of innovation that are defined as a technological trajectories. Of course, as Andrea was explaining before, technologies and also economics is about dynamics. And also technological paradigms is not stable over time. There are rare events that are called like the revolutionary periods in which there are paradigmatic shifts. For instance, an example that I always like to see, to tell about is the transition, for instance, between aircraft propeller and turbojet. So this, in this transition, this technological transition represents really a paradigmatic shift, because this changed the way an engine was designed, the way in which, let's say also the airplane was designed, the physics that was known and used, the technical and scientific limits that engineers that were working about improving this type of technology were facing. Of course, if we want to study technical change at the empirical level, so we need to find a way to empirically characterize and reconstruct this technological space. And in the literature, there has been, let's say, mainly three approaches. The first one was looking at the mapping of the performance output of the technology, because we would maybe this is sort of indirect way to think about the technological space, but we would expect that a certain degree of exploration are also reflected in the performance of the technology. The second approach is looking at the artifact characteristics, so characterizing the technological space more in terms of the product space. And let's say the last approach that is, I would say, the one that is mostly recently used and in which Andrea and I contributed the most, is to take more a cognitive level of analysis. And characterizing a technological space by the competence needed in a specific technology and how they change over time, the perceived technical barriers, so the technological bottlenecks, and the engineering heuristics, so the way, actually, the mechanism through which the agents explore the technological space. And one of probably, I would say, the success of this last approach is that data are sort of available for this type of investigations. Because indeed, patents contain most of these informations. In my career, I've been reading quite a number of patents, often together with the engineers, and especially in the first parts of the text. In the patent, you can find a clear description of the technical problems. Quite often, you have references to other solutions that maybe for certain way do not work, and then the explanation of the technical improvement. Of course, patents, more in general, are a rich source of information in terms of for the inventive activities, because they tell us about who is the innovators, both as in terms of the firm that is going to exploit the innovation, who are the inventors, where are they located, when this took place, and more importantly, patents carries information about citations to previous, both previous patents and previous scientific papers. So just in the logic of scientific papers, when you write scientific papers, you establish a bit the ground looking at previous literature. And there is a rich, there are a description of the invention, they are publicly available, and of course they are very flexible in terms of the level of analysis and the methodology that can be used. So, in particular, patent and citations networks can be used patent and citations can be used to build a directed network. And I could claim that this directed network is actually a representation of the technological space, because it's like a set of technical problems, and through this citation, you can look really at at the technological relations between them. And of course, as I was mentioning before, within this representation of the technological space, you need certain methodologies to find active areas of research. And one of the most used methodology is taken from bibliometrics, and this is the identification of the main flow of knowledge within the network. So I will not enter a lot in the details of how this is done, but the main idea is to find the set of patents and citations within this network that tends to connect the largest number of other patents in the network. So this represents the main flow of knowledge, so where most of the knowledge is actually accumulated. And this is consistent with the definition of technological trajectories. So beside skipping a bit the details, I wanted to show you some of the, like this picture that is the result of some work I did for my PhD thesis, and this is like the representation of the technological trajectory for the telecommunication switch in the industry for the periods between 1922 to 2003. And this represents like the unions of these technological trajectories calculated in a different time period. And what this graph tells us at a technological level, that basically before the 1999, that all the trajectories were nicely nested and cumulative. So it was just adding few years was simply building on the existing trajectories. While after 1999, this blue part, these patterns in the blue part became obsolete, and a new trajectory emerged. And if you read the patterns, basically this is a representation of a paradigmatic shift from circuit switching to circuit switching, to packet switching. So two quite different technologies related to data switching.
I'll take the mic very quickly. This is some work I did, well, it sounds very many years ago. This is the variation of the main path algorithm, that is to say, you vary the threshold, and instead of constraining the output to one single top path, that is the most frequently traveled path through time, from the bottom, the earliest years of the scientific explorations, to the top, and we are closer to the top. The top is closer to the present. You see patterns of exploration of the knowledge space, convergence when problems are solved, and very often the presence of complementary incremental innovations that are marginal steps in clinical practice that might really make the system converge around here. And that's when they understood, in this particular case, how to make particular devices work in the treatment of coronary angioplasty. These are papers, these are patents, okay? Again, a very early patent, some exploration, convergence when they solve some problems, and very much in the case Arianna found for a completely different industry, you do find that the system moves and as problems are solved, others emerge, and then the sequence really changes itself from within, with all sorts of implications for the entry of firms, the evolution of industries, and also the relevance of different skills. In this case, practitioners, nurses versus surgeons that might be able to use some devices and not others. There's been more work on that. I think there's still some mileage. I think we have little time.
Yes, I will go very briefly. So this methodology has been applied, and we've been thinking about several extensions. So it was applied to several other type of technology, which helped to have more external validations about the methodology itself. There was some work trying to find a different way to identify main flow of knowledge. So as I was saying, like you need to find active areas of research, and this could be conceptualized and measured in different ways. And obvious extensions would be, for instance, to try to build a network of patents, not based on citations, but for instance to use maybe text similarity, so really exploiting the description of the innovation of the inventions, and therefore to think to a different conceptualization of the technological space. This methodology has been also applied to try to predict the technological performance of certain artifacts, and of course, like patents could be linked to many other data sources to enrich the scope of the analysis. For instance, looking at a more individual level or scientific publication and products. And just to move on what we're currently working together is that we are interested in looking at the technological evolution of the technologies related to the fourth industrial revolution. So we just finished to collect patents data related to robotics, Internet of Things, and big data, and all these technologies seems to display a great level of complementarities in terms of their usage. If you think about the smart factory, it seems to need all of them. And we're interested to look also at whether we find these complementarities or common technological roots, looking at the underlying technological and knowledge level. And the challenge in this project is like the identification of more dynamic technological domain, looking at areas of technological opportunities, measure their pervasiveness and the relationship to also other technologies, and finally to really try to understand the extent to which these technologies are also at the technological level really revolutionary.
I think we should stop here. Thank you for your attention and for the invitation. We're more than happy to circulate the slides. There are another 2 slides about a couple of other projects we are doing with some multi-level data for you to read if you want. Thank you.
Thank you so much. Very, very interesting domain. Certainly this, network science applied to these domains is so fascinating. Thanks. Our final talk from the first session in the afternoon is by Erkan Kuruoglu from the CCNR. So the domain here is architectural heritage, so cultural heritage, and how data science can help in that domain. There we go.
Can you hear me? There's a photograph of me 10 years ago with someone during a conference, and everyone says, "Oh, I remember you singing in that conference," but I wasn't singing. Anyway, so do I have also paper? Okay, yeah. So I'm the last name here, Giancarlo. We are from CNRSD. I'm the only person from Signal and Images Laboratory. The rest of my colleagues, Cristina Padovani, Maria Girardi, Daniele Pellegrini, are all from Mechanics of Materials and Structures Laboratory. And this project is based in that laboratory. I'm a later addition to it. So, as the title says, this is about structural health monitoring of historical buildings. As you can see, correlation. Okay, we are in Italy, we are in Tuscany, and that's why it's such an important topic. But I don't want to scare anyone thinking that this is a civil engineering topic. It may sound like a civil engineering topic, but actually it falls under urban seismology. So it is, we are studying the structural health of a building, but the methods used are the methods of seismologists, the hardware methods. So the topic is an emerging and very hot topic. There are several cities, urban areas that are constantly being monitored. Probably most important is London and Barcelona. So the interest of the seismologists started with the motivation of trying to see the effect of earthquakes on buildings. And so we know that there's a big life cost of big earthquakes. The next expected earthquake in Istanbul is, well, the expectation is that 50,000 people will die, for example. Okay? So if this tower collapses, not many people will die by this. It is very important as a cultural heritage building. So other than the earthquakes, the other preoccupation is that there's an ongoing background noise, the vibrations. These vibrations are caused by humans, sometimes, like if there is a train passing nearby, or if there's construction work, or if there is a metropolitan underground station nearby. They seriously affect these historical buildings. So can we use the data that are obtained by seismologists to study the health of a building, and can we predict the effect of these vibrations on these buildings? Okay? It may still sound something very, very hardcore, hardware, and you are doing a PhD in data science. What's the connection? Okay, despite this initial slide and the motivation, the methodology behind, the soft methodology, is very much the same as what we use in information science and engineering. Okay? So I use the word information science on purpose as opposed to data science. Being also an editor, I have this problem with types. So what we are trying to do is actually uncover hidden information in data. So that's our objective. And data is the raw material that we use. And the methodology that we use for this is what we call statistical signal processing, or machine learning, or statistical or Bayesian machine learning. Okay? And we use data towards this end. Okay? So the nature of contemporary machine learning, or artificial intelligence, or whatever it's called now, okay, there are two approaches. One of them is supervised learning, the other one is unsupervised learning. So you start with your input raw data. So what happens is that somebody brings a huge bean bag of data and dumps it on your desk. It doesn't tell you much about it. Okay? And then, okay, you have some training data for which we assume to know the answer to your question. And based on that, you train your algorithm for the correct parameters. And then you hope that taking this algorithm, these parameters you apply to your input raw data, you will find out what you're looking for. Okay? If you're looking for cats and dogs and things like that. Okay? So the types of problems to which this is suited is like classification, regression, and so on. And there's then unsupervised learning, in which case you don't have your training data. Okay, again, you have your input raw data, and you pass through some algorithm and you find out actually the structures hidden there. But there is a game of words here, so it's not the full reality. Actually, you should have in your mind some classes of models. Okay? So this is not completely unsupervised. Okay? You have some prior information. You have some prejudice, as we call biases. Okay? So the nature of modern data is not so simple. Okay? It's not just a bag of data. And luckily so. Okay? Because there is a richness, a stratification of information. Okay? First of all, it's multivariate. So you don't take things, the beans in the bag, one by one. Okay? These beans are related. Okay? Because they grew up in the same soil. Okay? Their location is important. Okay? So relations between variables are important, like in financial data, biomedical, geophysical, seismics, urban seismology, okay, genomics, and so on. But this is not the full picture. And the other dimension of the problem is that in that bag that you are given, there are not only apples, but there are also bananas. Okay? And you have been told up to now that you cannot compare apples and bananas. But since I'm 5 years old, I said always, well, they are both fruits, yeah? So that's it. I mean, you should be able to compare apples and bananas. In a video stream, you have visual information, you have audio information, speech or music, and so on. So somehow you should be able to relate this data. Okay? So there comes the model then. The model is a network, and several talks today already mentioned this. So we have a system of interconnected things. And these interconnections are very vague to define. Okay? And you also have a graph representing these connections. Okay, so far so good. But that's not the full story. Data changes over time and space. Okay? So there are some causality relations. So in this general big bag, you are not given this perspective, but you should have this perspective. Okay? So what is needed is a time series analysis, or probably also spatial analysis, the location of things, location of variables. Okay? This is a very simple urban seismology signal. If I look at both frequency and time, you see how much richness of information there is. Okay? So we should consider time evolving networks. So not only the relations between different variables are important, but it's important how they change over time. And not only that, also how the relationship changes over time is important. That's how the topology changes is important. Okay? So back to the problem. Okay, we are talking about urban seismology. We have all these data collected with typical seismograms, spectrograms, and so on. So the classical approaches are like time domain methods, like eigensystem realization algorithm, or frequency domain methods like peak-peaking, frequency domain decomposition, and so on. And out of these, we get natural frequencies, damping ratios, mode shapes, and so on. But now, what we say is that you should do this in a multivariate way. You shouldn't consider only one variable at one location. You should consider across variables. Okay? So seismic displacement is important at different locations, but also probably other parameters. Okay? So the approach is, okay, sorry. The approach is operational model analysis as opposed to experimental model analysis. So you're not actively giving signals and looking at response, but you are looking at what's happening. You are just observing it. So there are already vibrations. Out of these vibrations, can I get information about the structure, the dynamic structure and health of the relay. Okay? So how many minutes do I have? Okay. So there are several objectives. So okay, you have a network of sensors to get your continuous long-term data, information vibration sources. You need to detect damages and you need to detect extreme events. Okay, this is a spectrogram from Barcelona city. Okay, this is actual data obtained by my colleagues from the Luca Tower. Okay, I will just mention in 2 minutes other application. Moving to general seismology as opposed to urban seismology. This is a project I have together with INGV and also Istanbul Technical University. We placed this station under Marmara Sea, near Istanbul, and we did multiple measurements, like seismic displacement in addition to gas emissions, for example. Again, we are using the same methodology, which is, as I said before, statistical signal processing. In particular, we are using sequential Monte Carlo methods. Okay? One thing we are interested in, both in the urban scenario and also non-urban scenario, is extreme event modeling. So you should drop all your Gaussianity assumptions. There was one talk earlier in the session said that we have actually so many millions of recordings, but we keep only hundreds of them, because only hundreds of them give us rare events, interesting events. And that's the case in most of the problems, especially in seismic events. All this main lobe, all these displacements, okay, I mean, they're a bit boring in the end because nothing happens. Things happen at the extremes. So can we detect extremes? And should we process really these millions of data points, or should we concentrate only in the text? Another project I have with Potsdam Institute of Climatology, Germany, using again the same methodology, exactly sequential Monte Carlo, extreme event detection. We are looking at climate data. And okay, this will seem a bit unrelated. This is what I did at Max Planck Institute in Berlin. We looked at gene interaction network using exactly the same mathematical model, sequential Monte Carlo, and this is what we obtained. This is how gene interaction will change over time. And we hope to get something similar to this also for the seismic data. Okay, this is one of my ex-students, maybe you know him, Mauro Costari. He's working on brain neural networks, again using the same method, same mathematical model, and same algorithms to solve it. And another thing I'm working, in collaboration with Fraunhofer Institute is how can we optimize the architecture of deep learning algorithms, deep learning networks. Okay, thank you very much.
Thank you, Arkan. Very interesting presentation. Okay, now we have a short break. I think we can reconvene at 3:30 something, let's say 3:35 at most sharp, we will begin back. We have the final session for today with two more very interesting talks by Alessandra Righi from INSTA to see the use of data science and big data for official statistics problem. And we have Pierluigi Lopalco on a close issue of epidemiology. So how can big data and data science help for epidemiological questions? And then the floor is, the stage is for 4 of our 8 students, okay? And this will be all for today. So let's get back in 15 minutes sharp. Okay, I'm the late one, sorry. So, the next presentation is by Alessandra Righi. Is Alessandra already with us? Yes, there she is. Alessandra is a scientist from ISTAT. ISTAT, for those the foreign people, is the Italian Official Statistic Bureau. And we have a relationship of collaboration with ISTAT for many years now, exactly on the topic of how to leverage and use big data for official statistics. And we've done several projects together.
Try to use.
How we try to use, exactly. But yeah, with time we learn how to do it, right?
Okay, thank you. Hello, thanks to everybody, thanks for the invitation. I will try to give you some brief summary of the ISTAT activity on big data, and in order to go fast to two examples of use on specific data and transactions. The use of scanner data, that is the most important one because it is already in production. And the second is a big challenge to use the financial transaction data in collaboration with Banca d'Italia in order to develop and use this information for several purposes. In particular, at the moment, they use in models and forecasting and nowcasting models. So I will show you first results of this assay. Well, there are since 2013 that ISTAT is moving along the study of big data, as Dino was already mentioned, because we of course discovered these important data sources, and we thought that we should improve the quality of our statistics data production with the use of these new important sources, several of these important sources. This is a map of we are developing in our institute. How can you see we use the most of the data sources, from scanner data to satellite images, from mobile phones to smart meters. With all of that, we faced several problems, especially in data access, of course, both for legal problems and for the need of the development of new partnership with new providers, or at least new actors in the context of official statistics. So all these projects have different level of development. At the moment, some of that are already we succeeded in produce some new indicators or new products, especially for scanner data and social media. We are in delay, for instance, for the use of mobile phone data. In order to improve and to try to give a new audience to these experiments, we decided last year to produce a new field, this of experimental statistics, that are that you can find in the site, in the institutional site, with a devoted page, where you can find all the data produced according sperimentazioni on big data, no? Experimental statistics on big data. This is a specific folder, and in order to try also to providing evidence of this study, especially to have a feedback from the users in order to try to decide if there are important advanced or we have to consider them at least experimental and not official statistics. So ISTAT decided not to produce the new product made with the big data as official statistics, with the only one exception, that is that of the scanner data that we will see. There is also a big data committee annual report that we produce, and where you can find a summary of main activities developed in the latest years. Okay, coming to scanner data, you can see, I don't know how of you are familiar on this topic, so I put a definition of what is this kind of transaction data. Are those data obtained from retail chain contain data on turnover quantities per item codes. This item code is a GTIN. This is, as you know, the barcode, and it gives a lot of information on the products and on the prices and so on. So scanner data is that decided that can be used to replace the price collection in hyper supermarkets, and in the future, near future, also from discount and other kinds of point of sales. For instance, clothing stores, home electronics, and so on. In 2018, ISTAT introduced this kind of scanner data of grocery products in the production process of estimation of inflation. As you know, I suppose the consumer price index is one of the most important macroeconomic indicators in our country and also generally speaking. So this is a very crucial point. The introduction of a new source like scanner data that has, how we will see, that has still some problems in the data access, is considered an important step forward in the usage of these new sources. This innovation concerns 78-80 indices and belonging to products according to the ECO division. This is a statistical classification, important statistical classification. In this year, in agreement with two groups of two partners that are the retail trade chains, in collaboration with this association of modern distribution, the Nielsen, this is a firm, gives to ISTAT data for 2,000 outlets covering the entire national territory and monthly collected by ISTAT on a weekly basis by item code level, So this is almost the complete framework of the supermarket and hypermarkets in Italy. At the moment, we use a static approach in the usage of this source. We adopted a sampling of items similar to the traditional price collection method. That is, introduced a cut-off sample of the barcodes, and we use 1.8 million price codes weekly, and then we aggregate these weekly prices at the monthly level. Those those are the two main streets, main roads we will pursue in the next years. We want to go toward a dynamic approach in the sampling of these barcodes in order to have a complete, full use, a full benefit of the usage of this source, because we could have much more information, much more barcodes to use. And this is, it takes two types of improvement. One in the field of the sampling, on the technique of sampling, and the other on the, of course, on the treatment and pre-treatment of this data coming from the Nielsen. So are both important in going toward this dynamic approach. The second is the use of the information on the space, that is, it's possible to compare, according to this source, prices of the same GTIN traded by several retail trade channel, different by geographical area. And in this way, it's possible to build spatial index, that is, for instance, the purchasing power parities. This advancement can improve the compilation of these international PPPs and also solve the issue of compiling subnational or regional PPS across different areas. How many minutes? Still 3 minutes. Okay. Very, very rapidly, I go to this new source that is the financial transaction data that can be defined data from debit and credit cards and zero transaction, that is bank-to-bank transfers. In collaboration with Banca d'Italia, we try to use two sources that are the transaction of the exchange circuit of and interbank settlements of the system, European system of payments, and data from the anti-money laundering aggregates reports that this is called SARA from the UEF of Banca d'Italia. The goal is the production of new series of indicators useful for nowcasting and forecasting macroeconomic aggregates. These are the information we collected according to different sources, the BComp, target doer, that is credit transfer, debit and payment cards, ATM and POS, checks and other. And this is the information from the SARA system that are also disaggregated by sectors from which the payment originates. As you can see, the first results, these are the GDP series from the 2003 and up to now. And as you can see, there are a similarity in the trends between the two indicators. This is compared with subset of the series of SARA source. So first results show that the new source systematically analyzed for the first time give positive evaluation on the use of this service for both for early estimates of value added and turnover in services in national accounts system, or forecasting models of private consumption in the context of official statistics that has, of course, very strict rules and what I have to do? Well, this could effectively use in nowcasting and forecasting activities, and this is quite different from the normal construction of models in official statistics. And we will continue this work on the basis of this new Eurostat project on big data that has a work package specific on financial translation. And the goal of this work package is to try to use this information, specifically data from credit cards, to the goal to improve the statistic on tourism, on some of the items of the household budget survey, and or macroeconomic indicators. So I hope that someone of you can be interested in try to take on board to this work package. And so thank you very much for your attention.
Thank you, Alessandra. We now have my colleague Pierluigi Di Palco from University of Pisa. Pierluigi is an epidemiologist, a medical doctor, with a long history of work in many topics connected to epidemiology. And we
Yes, I can use this. Yeah. Hello. So we will talk about a very different topics. That is public health. So the first question is how can So we can talk about a different topic that is public health. So first question: how can we relate data, numbers, figures, to promote health and to prevent disease? So this is the big question. And I have to tell you that we can start with a very old story. It's a story of a pump and a handle. And this is a story of cholera in London. So this is the end, the second half of the 19th century. In 1954, there was a large outbreak of cholera in London, and there was the first epidemiology in the modern history, that was John Snow, that just looked at the map. And on this map, he just designed these dots and observed the dots. The dots were people dying from cholera. And he observed that some of these dots were clustered around a pump, this blue dot here, and were not clustered around the different pumps. And without knowing anything about bacteria, about the real cause of cholera, he just asked the local authorities to remove the handle of that pump. So from data, he took some knowledge and started an action. And this is the sense of epidemiology, is data for action. And this action saved a lot of lives. Many years later, there was Robert Koch that understood the role of a bacterium. So data were more powerful than the direct observation of the bacterium to save lives. And this is the real topic. And this was not the first time. Again, here we are in the late 70s, and this woman is Sandy Ford. She was a woman just processing some data on drug consuming in the US, and she realized that there was a very strange peak in the consumption of a very rare antibiotics. It was pentamidine. So this woman was the first in the world that realized that something were wrong, and she discovered the start of the AIDS pandemic in the world. It was 1979, and the CDC understood that something were happening, and it was AIDS, and only a few years later there was the isolation of the virus. Again, the data came before the isolation of the virus. But which data can we gather? Today, what we call disease surveillance, infectious disease, is just a very, very rough collection of data that are coming from the GPs, the general practitioner, that are coming from the hospitals, that are coming from the lab. And then very, very usually we have just paperwork that is collected through computers and then is processed by people. So it is a very time-consuming system, not only, but this is, for instance, an exercise that we made here in Tuscany. These are the data related to pneumococcal disease. Pneumococcal is a very nasty disease. It's a meningitis, sepsis. Many of these people, many of these numbers die because of pneumococcus. And what we discover is that if we take the data from one source, that is a regional laboratory network, we take the data from another source, that is the national surveillance from the GPs, and another source, that is the hospital discharge record, we realize that only few of these records are simultaneously present in all the sources. So it means that if we take just one of these sources, we cannot have a real idea of what's happening in the population. And it is very, again, time-consuming to combine all these sources. What we know that we see with this surveillance system just the tip of the iceberg. In the specific case, we ran some sophisticated analysis model for the analysis and try to estimate the real burden of disease, just observing these different data sources. And I can tell you that we collect the data only on 74 cases. So we know the existence in Tuscany of 74 cases of pneumococcal disease, but in the reality, according to this model, the reality is completely different. It is almost 500 cases. So our system has a completeness level of barely 13%. We can improve this system. We can improve the system because the data is there, but we need to find and figure out a system to link this data, analyze this data, and possibly make some automated model for analyzing this data, because the data are there. And now the situation is pretty much complicated, even for infectious disease, now that you know it's just one bag that is jumping from one person to person. It's not like that simple. For instance, this is at the European level. The European Center for Disease Control is collecting data on mosquitoes. Mosquitoes are really a new problem for public health. This is the distribution of Aedes albopictus that is, you know very well, it's the tiger mosquito. The tiger mosquito is spreading all over Europe, and together with the spreading of the tiger mosquito, there is also a spreading of some viruses that we didn't know before the tiger mosquito was in Europe, like chikungunya, for instance. So new diseases are coming. To forecasting the spread of the disease, we should forecast, so not only the data from the human health, but also the data from mosquito spreading, but also the data on climate, because mosquito and climate are quite correlated. And this is a similar map saying that another very, very bad mosquito is just here, is not present yet in the central and the southern Europe, but is here and probably will come very soon. And this is the Aedes aegypti, that is a vector for very nasty diseases like dengue and other mosquito-related viral fevers. So, again, we don't have only data on the computers in the labs. So we have the data on the computer in the labs, and we cannot access easily those data. But we can eventually take information also from the social networks. This is, for instance, an example where if you use the Google Trends, so the search terms on Google for influenza, you see there is a quite good fit with the real influenza cases trend during the different years. So these are in orange. You can see the Google Trends, and this is the real peak of influenza. What is interesting is that the Google search are anticipating what will happen. So we could eventually anticipate over almost 1 week the real peak of influenza just looking at Google. It's not that simple. There are a lot of research ongoing, but as well as for flu, we can perform similar analysis also for other diseases. Not only infectious disease, again, do you know, probably you don't know how hard it is to assess the burden of cancer in any country. This is Italy, but it is the same all over the world. To set up and maintain a cancer registry is a quite burdensome system. You have to collect information from the hospital discharge record, from the patient medical record, from the cytological lab record, and unfortunately from the death certificate. And today, all this work is done manually. There are people sitting around a table, very often also using paper, because some of the clinical records are only on paper in many hospitals. But again, most of these data are on some computer somewhere. What is important now is to improve the technology and to link each other, all these data sources. And imagine if you can link these data sources on the cases of cancer with, for instance, environmental data. This is the map of radon. This is a cancerogenic natural gas that is present in many areas. So imagine that you can compare the distribution of radon data or the distribution of the air pollution monitoring. Again, the air pollution data are data that are routinely collected, so are on some computer somewhere. And it would be very interesting, for instance, to link together the air quality data with healthcare databases to see if there are connections, or eventually also to forecast which effect will have on healthcare the quality of the air in our cities. So the message is this one. There are data that we can analyze. Now again, before we were talking about embedded CPUs in our houses. So imagine that we can eventually extract data on the food that people are consuming, or just food that they are buying, and making some relation with their health status. And finally, this is also a new development, because a very important determinant of health is the human behavior. We can strongly affect our health status according to our behavior. And it is important to study the human behavior. I make you an example. This is vaccine coverage. And these are vaccines against very old diseases like polio, diphtheria, tetanus, etc. And this line is the vaccination against measles. So all of these are very nasty diseases, and consider that 1 drop in coverage means 5,000 children. So every 1% drop is 5,000 children. 5,000 children that are not vaccinated, that are exposed to this infectious disease. So starting from 2012, there was a very strong drop, especially for measles vaccination, and this could be eventually prevented if they observed, again, Google Trends. These are Italian people that are searching on the internet the search term measles and autism. So this is the point in time. It was 2012 when these fake news on vaccines provoking autism was actually spreading in Italy. Very late in comparison with other countries, but it happened and it was registered somehow on Google. I don't have time to explain why, but I can tell you that here there was the public distrust towards vaccination that was reflected in a vaccination coverage drop. And again, this is something that we explored on Twitter. This is social media listening. So again, some machine learning analysis on data on Twitter that again showed some attention and some very, the red one are the negative tweets, some very negative sentiment towards vaccination that was following the start of mandatory vaccinations in Italy. So I stop here, and I hope that eventually, I mean, there are these topics that are of some interest for you, and you are somehow interested in collaborating for making some in-depth analysis of data related to health. Thank you.
Grazie. Thank you, Luigi. Yes, certainly public health, it's a very hot issue where also we have ongoing collaborations, and I think it's very promising venue for data science work. Now we have the final session of the day. The stage, as I said, is for our PhD students of the first cycle, so those that are now in the second year. Today we have Elisa Ferrari, Luca Insolia, Cecilia Panigutti, and Tommaso Radiccioni. The four of today. Elisa, the first one, will update us on her work in the analysis of MRI signals and other medical data in autism.
Okay, thank you. Should I need the
Questo. Dovrebbe essere acceso.
funziona?
Sì. Mettilo vicino.
Okay. Hi everybody, I'm Elisa Ferrari, and today I'm going to present you my PhD project titled Brain MRI. MRI stands for Magnetic Resonance Images, Signals and Gene Expression in Autism Spectrum Disorders. So the team is quite heterogeneous. My supervisor are Alessandra Retico, Alessandro Cinerina, and Davide Bacciu, so a physicist, a biologist, and a computer scientist. Okay, let's start with some basic information about the disease, autism spectrum disorders. During this conversation, during this speech, we will talk about ASD, just for simplicity, or also about autism, okay? So autism is an extremely heterogeneous neurodevelopmental disorder. It involves communication and social skills, and it is characterized by repetitive and rituals movements by the subject. Symptoms can show up in the first 6 months of life, but becomes explicit after 3 years of age, of course, because given that this disorder involves communication skills, it becomes more evident when the child starts to talk. It affects more or less 1% of the population, with a clear prevalence in male subjects. It is highly irritable. This has been proved by various family and twin studies. And as of today, neither causes nor treatments are known for ASD. However, there exist some programs that can improve the quality of life of the patients, but for them to be effective, it is absolutely important an early diagnosis. So we basically need some quantitative biomarkers that simplify the diagnosis, that today is just a prerogative of the psychiatrists specialized in the disease. So as you have probably understood from this just very short presentation, we can study autism basically at 2 levels, at the brain levels with neuroimaging and at the genetic level. Okay, let's start with some information about genetic research. So we can basically perform 2 kinds of analysis. We can study DNA sequencing. That means that we are looking at which variation in the DNA occur more frequently in the AST subject with respect to the else ones. Of course, the variation can be at different scales, so macroscopical or very little. Or we can perform an analysis studying the gene expression. Okay, so the gene expression is the process. This is a cell, and this is the nucleus of the cell that contains the DNA. Gene expression is the process with which our cells, basing on the tissue they belong, so it's a tissue-specific process, they read and interpret a portion of DNA to synthesize proteins. Okay? So basically, studying gene expression means that we want to understand how the information coded in the DNA influence the behavior of our cells. Okay? So in this kind of study, we usually analyze this quantity called transcriptome that show which genes and how much do they regulate the gene expression process. And we can basically try to answer to two questions. Which genes are more expressed in a specific tissue in ASD subjects with respect to the LC1, and how does gene expression vary across various tissues in the ASD with respect to the LC subject. Okay, so I've said you before that autism is a highly heritable disease, but the fact is that we still don't know very much about the genetic causes of autism. This because we actually believe that autism, as many other psychiatric diseases, can be explained with a multifactorial threshold model. What does it mean? It means that we believe that the variation causing autism are not present only in the autistic subject, they are present also in the healthy population, but the ASD subject presents a highly number of this variation. So these models also explain why we have to call it a spectrum. So why we have so many various kind of severity in the autism disease. And why do we have a broader phenotype? A broader phenotype is a class of subjects that present some of the symptoms of autism, but it's not diagnosed as autistic. Okay? So, as you can understand, studying autism, studying a disease that can be modelized with a multifactor threshold model, it's very difficult from a genetic point of view. Actually, in the literature, we find that there are some good, interesting results studying gene expression, but the fact is that studying gene expression, you need to have a tissue sample of the subject, so the database are very little, and the kind of knowledge that you can acquire with this kind of study is not useful to find a diagnostic biomarker, because if you want to diagnose this disease using this information, you have to take from him a tissue sample, so it's quite difficult with living persons. Okay, so let's keep to neuroimaging research. Also, in this kind of analysis, you can analyze two kinds of data: structural MRI and functional MRI. So, structural MRI basically show you the morphology and also various properties of the brain tissues, while functional MRI show you the spatial and temporal distribution across the brain of oxygenated blood. That is a way to measure our neural activity, let's say. Okay, so the main problem here is that the biggest database containing ASD data contains more or less 2,000 MRIs, and one MRI is composed by 300,000 voxels, and for every voxel in a functional MRI you have a time series of about 1,200 points. So, of course, if you want to perform a classification task between healthy and ASD subjects, you are in an overfitting condition. So you have to heavily compress this data with various steps. And we don't know anymore if in this feature extracted after all the steps, we have still the information we want to understand, we want to study. There is also another important problem, that is that the data in the biggest database, but also in the others one, have been collected by various sites, by various hospitals, research centers. And thus they have been acquired with different acquisition modalities. So even after all this preprocessing, that reduction, and other kind of steps, the machine learning algorithms are still very sensitive to the differences due to the acquisition modalities. So with so little data set, it's unavoidable that in your training set there is a bias due to the acquisition modalities. And basically the results obtained in literature are, let's say, corrupted by this bias in the training. Okay, so this is the point that I was talking about. Data strongly depends on the acquisition modalities. So just to summarize the problems, we have that in the genetic part, the difficulty to assess the role of genetic variation in autism because of the nature of autism. And for what concerns the gene expression studies, we have that the result obtained cannot be used to determine a biomarker used for diagnosis. While in the neuroimaging part, we have that, basing that we don't have any a priori knowledge on autism, we have to analyze the whole brain. So we have a lot of data, and we have a lot of features, and we have a very little amount of data. So we are this cause overfitting. We have to compress this data, and at the same time, we have the problem of the bias that I was talking about before. So my PhD project wants to try to solve these problems, trying to connect these two fields. And this is possible because gene expression varies across the brain. So we can basically find which regions are more differentiated between autistic and healthy subjects with gene expression, and then looking at them with neuroimaging. So I want to use gene expression as a feature selection for my analysis. Okay, so this is the outline of the project. So the first part is what I was talking about before, gene expression analysis to detect brain regions relevant for ASD. Then study these regions with machine learning algorithms. And in particular, I want to perform these two kind of analysis. I want to avoid data manipulation using contextual graph Markov model. That is basically a method that consents you to handle very structured data in your machine learning model. So I want to represent every subject with a graph in which the nodes are the fMRI signals, and the edges, fMRI stands for functional MRI, and the edges gives us some spatial information. And the other point is to avoid learning from bias, and this can be done using a special loss function that has been described in this work, that basically doesn't want only to maximize the capability of your model to distinguish between autistic and controls, but wants also to minimize the capability of your machine learning to distinguish between subjects coming from different acquisition sites. So it's a saddle point research. Okay, so this was the project. I'm running out of time, I think. Okay. Here there are just a few slides about the update for the PhD board, but let's say just easily that I have downloaded 2 of the 3 databases that I have to work with, and I've started some analysis. And I focused these last 3 months working on the last point of my project, because I think it's the most hard one. So this loss function actually doesn't work very well in my case because it works well when your bias is not very strong. And in my data, I have I have a very strong bias. So this tug of war between maximization and minimization actually doesn't let to my net to learn anything. So, okay, we can skip this presentation. Anyway, I'm working with I'm working on another loss function with penalization that I write by myself, and it actually works. But I would like to extend this analysis also to other databases to see if it works, if it is generalizable enough. Okay, so, thank you.
Thanks, Elisa. Thanks for the update. Now we have Luca in Solia. In Solia is, well, I didn't see it. Elisa is a physicist by background. And Luca is an economic statistician by background. And Luca is working on methodological aspects of data science, in particular robust model selection for very high dimensional data. That is what he will be telling us shortly. I think we should thank Vittorio, because without him we would never seen
Sì, sì. Sì. Sotto il terzo lavoro. Si limita solo le colonne, quelle confezionate. Hi everybody, and I guess you were wondering what's this coral-like image in the background, and it is actually an artistic representation of the human microbiome created by the artist Rogan Brown. And we will deal with this high-dimensional problem where we can imagine each of these bacteria, or perhaps group of bacteria, as being one of our features in a regression problem. And we propose to apply statistically robust model selection techniques, which are also called feature selection or variable elimination, in order to identify the most relevant group of bacteria affecting our outcome, which might be phenotypical or a clinical outcome.
Luca, keep it to the closer to you.
This is okay, just to provide you a quick overview about what has been done in model selection in the last couple of centuries at least. Until a few decades ago, the most popular approach and probably the optimal one was to perform what's called the best subset selection. So if you have an n-dimensional model, you can try to fit all possible submodels of any size. Of course, this approach wouldn't scale up as the model size increases, and many researchers in this time were questioning the possibility to solve the problem optimally and efficiently. But in 1996, Lasso has been introduced, and it is a very efficient algorithm because it's relying on a complex formulation. And so even larger class of models that were possible were addressed, but perhaps non-optimally because it requires very strong assumptions to obtain an optimal solution. And 20 years later, the old approach of best subset selection has been formulated as a mixed integer optimization problem, and it fasts the computation quite a lot. What we consider didn't receive much attention in the literature is the case where the data have some contamination that I will describe soon, or missing values. So just to clarify the model, we will work with the simplest class of models, or linear models, also because we are not really interested in predicting the outcome, but mainly on the interpretation of the result, so in identifying the most relevant features in our metrics. And they already discussed this assumption, but we are also interested in some more that won't be the focus of this talk. For instance, the size of the X matrix or possible collinearity structures inside of it, the presence of missing values, and how to perform the inference after you select a model. So we can think to have the availability of an oracle which suggests us the relevant features. So these are the non-zero coefficients, and at this point the problem is solved. We just have to extract the corresponding variables in X and fitting them using least squares, for instance. But in a realistic scenario, we don't know which and how many coefficients are non-zero. Thus, there's no such a dichotomy, zero or non-zero coefficients, but we would have most of them to be negligible and some of them to be truly important. And in our case, the problem is even more difficult because we assume that we might have some contamination in our data. So just to provide you a quick overview about model selection, the oldest approach of best subset selection can be formulated using this mixed integer program, where you specify a pseudo zero norm on the vector of coefficients, which defines how many of them are allowed to be smaller than a p, so the number of variables in the final model. And it aims at obtaining the optimal solution, and even stopping the algorithm earlier, you can obtain an approximate solution. But on the other hand, even if it's much faster than the combinatorial evaluation of all submodels, it's still time-consuming. And it doesn't really work well when the data have some difficulties, for instance, strong correlations or low signal-to-noise ratio regimes. And for what's important, mainly important to us, is that it is not robust because it is still relying on least squares. And even before the introduction of that problem, Lasso is actually the same problem, but instead of the L0 norm, use the closest convex relaxation, which is the L1 norm. And elasticnet is a generalization of Lasso. This is the Lagrangian formulation, where you can see that there is an additional parameter alpha, which specifies the trade-off between a Lasso solution and a ridge solution. And it is still a convex formulation, so you can compute it very fast. It is well known that the estimates are biased and is not so time-consuming to tune the two parameters, but again, it's relying on least squares, so it's not robust. And what we mean by robustness is clear from this example. The red line is the least squares fit, and is attracted by these points at the bottom. And this happens because these are influential points. So it means that the estimates are disrupted only by 10 points, while the blue line, which is a high breakdown point estimator, is not affected by them. And this happens because it fixes in advance a trimming proportion of units, so in this case it's downweighting 50% of the units, and is not affected by them. On the other hand, there's a price to pay in order to obtain an high breakdown point, and it comes in terms of efficiency, because throwing away 50% of your data when only 10 of them are outlying, of course, will increase the variability of the estimator, so reduce its efficiency. And talking about the 50% breakdown point doesn't really make much sense if you don't know the contamination that you have in your data. This is the usual contamination model which was introduced in the 60s, and it specifies that each row is contaminated with a small probability epsilon. So as long as epsilon is smaller than 50%, you shouldn't have any problem. But for high-dimensional problems, this is not so reasonable. So in 2009 has been introduced the cell-wise contamination mechanism, which is essentially the same, but it's working independently for each variable. So for each variable, you contaminate an epsilon proportion of unit. And the total amount of observation with at least one contaminated cell is equal to this number, which will easily become larger than 50% as the dimension increases. So the old approach based on case-wise contamination usually works in this way. They start using an R-trimming approach, so for instance they fix at 50% at the breakdown point, and to recover as much units which are typical as possible, they perform a second step in order to include them in the fit. And it's also interesting that also this estimator has been formulated using a mixed integer program. And in this way, you can obtain such nice properties, but on the other end, you don't obtain a sparse solution. You cannot deal with cell-wise outlier, but these authors propose to deal with it using a reprocessing step, using missing data treatment techniques, and heuristics works pretty well. And again, they're not stable if there are strong correlations with the data. So what happened a few years ago is that they matched these two approaches, model selection and robust statistics. So you can look at this solution in two ways. Either you take a robust estimator and you add a penalization, or you take a penalized method and you change the least squares loss function with a robust one. And this is what they did. So they reach an high breakdown point, but they are not efficient. And in order to increase the efficiency of the procedure, they perform a reweighting step and use this kind of estimator. So again, they have the pros of robust estimators, but on the other side, they still cannot deal with cell-wise contamination, and they also become computationally heavy because of this reweighting step. And this is what motivates our research. So the most general question we are trying to address is how can we understand which estimator or model selection techniques perform better and under which scenarios. And in order to address this question, we are running simulation just to see the results from an empirical point of view, but also from a methodological point of view. And to be more specific, we are trying to combine different existing methodologies. For instance, we are wondering if we can match the mixed integer formulation to subset both the variables and the units, or if simply we can just switch the reweighting step in the robust penalized techniques using the forward search in place of the estimators, which is in use in all the estimators I described. And using some simulation, we can see that for case-wise contamination and fitting a larger set of models, just changing the forward search to the estimator brings a slightly better false positive rate, and it's also a bit faster. But the computing time is not considering the time needed to obtain the raw solution, after which we would reweight, so to increase the efficiency. And this is important because we also talked about a three-step procedure, so we subset the problem into three procedures. Imagining to have this data with contamination, on the first step, we can run an high breakdown point estimator, either supervised or unsupervised, just to flag the contaminated units and throw them away at the moment. At this point, hopefully we have a clean data set and we can run the classical feature selection algorithms, for instance ElasticNet, so we will subset even the columns. And at the end, in order to keep as many typical units as possible, we can run, for instance, a forward search to recover efficiency. And if we include these trials in the simulation study, we can see that using a robust clustering algorithm or a robust BCA methodology, we have a strong we have much better false positive rates, and the elapsed time, it's a bit higher for robust PCA, and it's comparable to the other techniques for robust clustering. But again, these two lines, the brown and the pink one, they don't include the time to obtain the raw solution, so the one with only an hyperatomic one. And we were also wondering, there are only these two mechanisms existing in the literature which are in use, and we were wondering if there are any which can be more realistic in a dimensional problem. And also we are trying to use this robust model selection techniques to the missing data treatment problem. And as I mentioned at the beginning, it's also interesting to apply these techniques for investigating the human microbiome. These are only two possible research questions that we would like to address. And using feature selection techniques, we can identify the most relevant bacteria affecting these outcomes. And using robust techniques, we can identify the atypical units, which might be patients or different tissues where the samples are taken from. And we propose to address these questions using publicly available and privacy-preserving data. For instance, this is a large consortium which offer a large amount of metagenomics data. So in conclusion, we propose to merge the three different branches of statistics, or at least what they are considered separate, which are model selection, robust statistics, and missing data treatment, and to apply these techniques to the problem, to the investigation of human microbiome. This is it.
Thank you, Luca. Of course, we also have in our diverse PhD, we also have theses that are more methodological than others that are more applied. But we also appreciate the fact that you're trying also to figure out an application domain which is compelling and interesting for your methodological advances. A similar thing is also the approach is also in Cecilia's thesis, which is addressing some fundamental issues of machine learning, namely explanation of machine learning models, and also application in a particular domain, which is health, and in particular medical diagnosis. How to develop methods for prediction decisions that are also comprehensible in human terms. Here we are, Cecilia.
So hi everybody, I am Cecilia Panigutti, and today I will show you a bit of my research, which is on explainable AI, and in particular on explaining black box decision for healthcare decisions, healthcare applications, because this is what I'm interested in. So, as you heard also from the previous presentations, machine learning is right now changing, reshaping several industries, and it's a really active field of research. And so it is also at the core of many decision support systems. And how this model works, they try to learn to generalize from examples. So, for example, if we want to build a diagnostic decision support system, then we have to have a long history of several patients with their clinical history. We feed it into machine learning models, so that when a new patient with its data, a new unseen patient arrives, we can predict his or her diagnosis. So one thing that most of these decision support systems have in common is that the machine learning at their core is a black box, which means you cannot inspect what the algorithm has learned. And this is a problem for several reasons. First of all, for trust issues, because physicians might not be so willing to accept a recommendation made by a system that they don't understand and which is not able to explain itself. And also because biases in the data easily mislead machine learning models. And to further motivate this last point, let me tell you about this cautionary tale of how things can go wrong when you deploy a black box in the real world. So this is an example taken by this paper from Rich Caruana from Microsoft Research, and he and his colleagues were trying to develop this algorithm, which thankfully it was interpretable. But this model was supposed to help physicians decide if pneumonia patients needed hospitalization or not, because hospitalization is costly, so they want to have an algorithm that was able to help physicians in this decision. And this algorithm was assigned to each patient a risk score of dying from pneumonia. So this was a high-performance interpretable model, so they were able to find out that the model actually had learned that if a patient arrives at the hospital with asthma and pneumonia, then he or she has a lower risk of dying from pneumonia. And this doesn't make sense, because if you have asthma and also have pneumonia, you have a higher risk of dying, of course. So, but this was a real correlation present in the data. The fact was that there was a data that was missing, which is, okay, if you arrive to the hospital with asthma and pneumonia, then you are immediately sent to the ICU, which is the intensive care unit, where you receive a very aggressive treatment that actually lowers your chances of dying from pneumonia. But it's not the fact that you have asthma, it's the treatment you receive. So if you use this model to, if you deploy this model in the real world, you can see how things can go really wrong. So how can we open the black box? This is a taxonomy of the problem made by our group in a survey. And the main split is just about dealing or not dealing with black boxes. So you can build a transparent box which you can inspect, as Caruana did, but you are actually restricting yourself to a specific kind of models. So we don't want to do that, because if we use black boxes, it's because they have higher performances. So we want to use a black box. So if you want to open a black box, you can do that in several ways. You can do model explanation, where you try to explain the global behavior of the model. Or you can do model inspection, so build a technique which is specific for your model. Or you can do outcome explanation, which is what we are doing. So you try to explain just one instance, one particular instance, the outcome for one particular instance. And what's the intuition behind this kind of explanation techniques is that the first paper we talked about that was Ribeiro with Lyme, if some of you know about it. And okay, if we want, even though the decision boundary learned by the black box in the feature space might be complicated as one, if you want to try to explain just one single instance, which is the red cross here, then if you zoom in into the feature space in the neighborhood of that instance, you can always approximate the decision boundary with a simpler and more interpretable model. And that's where you take your explanation after. So, okay, we want to solve the outcome explanation problem for multi-label classification tasks. Because usually in healthcare, for example, in a diagnostic decision support system, a patient might have more than one condition, so they are not mutually exclusive. So it's a multi-label classification task. And we addressed this issue with Marlena, which is a technique that we presented 2 weeks ago at the AAAI, which stands for multi-label rule-based explanation, which is a technique able to find an explanation for the multi-label black boxes. And it solves the outcome explanation problem because it is agnostic with respect to the black box algorithm it is trying to explain. And it is locally faithful, it's not globally faithful, just locally faithful. So, just in 3 steps, how Marlena works. So first, it generates a synthetic neighborhood around the instance to be explained in the feature space with a strategy suitable for multi-label decisions. Then, on such synthetic neighborhood, it learns a decision tree, and from the decision tree, we take a decision rule, joining the split condition from root to leaf for that particular instance, and we have our explanation, which is a decision rule. So we perform a lot of experiments with several datasets. I'll just take this one, which is the medical datasets, which is a corpus of fully anonymized clinical notes with their associated ICD-9 code, which is the code that is assigned to each disease. And so in this case, we are trying to explain this black box. The task of this black box is we want to map the words into the clinical notes into their ICD-9 code. So the question we are trying to explain is why this particular clinical note was classified in this way by the black box. So what Marlena do is take this note and try to find the words that the black box looked at to make its decision. So this is an example of an explanation by Marlena, and we can see that it's a decision rule, and it's saying, okay, there was no mention of duplication, no mention of reflux, but there was mention of hydronephrosis, normal, paliectasis, and mild. So the black box decided that this clinical note was associated with the ICD-9 codes of urinary incontinence and hydronephrosis. So what about the future work? Marlena works with tabular datasets, so it's the first step towards this. It's just the first step, a preliminary step. And we want to try to extend Marlena to explain other kind of datasets, for example, time series datasets. There is this algorithm which is called Dr. AI, which was developed by Edward Choi, which is a recurrent neural networks which takes all the history of a single patient and it predicts the diagnosis, the future time-step diagnosis. And it's a strong multi-label datasets, and also, it's a time series data, so we have to extend this work here. And then another thing we want to do is trying to explain the causal relationships learned by the algorithm. Okay, so what does it mean? In the example that I showed you before, where there was a correlation between patient having asthma and lower risk of dying from pneumonia. Okay, there was a missing variable, which was the aggressivity of the treatment, which is the real variable that is causally influencing the risk outcome. So maybe since we are using our algorithm to make decisions, we need to understand how they are reasoning. So can we unveil the causal structure learned by the black box? And this will be the explanation for the black box. So this is it. Thank you.
Thank you, Cecilia. Good report of the state of affairs. And yes, tomorrow I think we will be discussing even more about this topic. But actually, this fact that mostly machine learning and AI up to now is based on correlation reasoning, right? Statistical correlation and association, and how to move forward to instead not simply correlation learning, but causal learning is one of the frontiers, right? Because we humans actually reason more based on cause and effect reasoning rather than statistical correlation. But this is not what the current AI systems do. And this is really one of the big frontiers that we as data scientists need to face. Probably more and more, experiments in collecting data may reflect the causal structure of phenomena. And we must become able to do causal reasoning and causal inference on the new forms of data that we are collecting. Now, it's the final presentation for the day. It's been a long, I hope also fruitful day. The final topic is misinformation. It's again a topic that bumps again into the discussion. And Tommaso Radiccioni, who's doing his PhD work on around this topic, will talk about how to put together a multidisciplinary approach to the study of the diffusion of misinformation in our information system, and especially online media. Let's see if we have also this final lecture. Okay.
So, Mark? Just keep it close.
Yeah. Okay. So, Okay, so good evening to everybody. In this short talk, I'm going to talk about the PhD proposal which I'm working on with the MT researchers are present here this talk, Tiziano Squartini and Fabio Saracco, with Guido Caldarelli and Elena Pavan from Scuola Normale. And the topic of my PhD proposal is information diffusion and our multidisciplinary approach for the study of its impact on social media. So starting from the very beginning, I would like just to briefly mention some reason why we are working on misinformation, because basically everybody is talking right now about misinformation diffusion and its impact on society. For this reason, in 2016, the Oxford dictionaries talk about post-truth as the word of the year, and even academic researchers, governmental institutions, and mainstream media are talking right now about misinformation. So I'm talking about misinformation, not fake news. It's not an error of mine, but it's a choice to not mention fake news, because this term is not able to capture the complexity of the entire problem, because first of all, fake is a part of a discourse which is broad and is part of the what is called bias, cognitive bias, that is the way we think something as true or fake. And because this term is associated by from the public opinion to partisan political debate, and it is appropriated by politicians as Donald Trump to undermine the credibility of media and journalists. So it's a term that I don't like really much. Misinformation is a broad term, actually, because during the years there are a lot of publications and papers about misinformation, and for this reason there are even a lot of similar terms such as rumors, urban legends, propaganda, and even disinformation, which is really similar to misinformation. The definitions are really a huge number, but there are few common aspects to define what is misinformation. So misinformation is basically a news with the which is content is inaccurate and the intent is malicious, as reported in a recent report of the European Commission. The diffusion of misinformation is really large, so the misinformation can create large-scale cascades and cross-platforms sharing patterns, and the narratives on misinformation news is distorted and it creates a precise vision of the words and the reality. This problem is not new. As before I said that in 2016 post-truth was the word of the year, but is as old as the newspaper industry. Now I would like just to mention briefly this story, because it allows me to talk about the social media diffusion, misinformation diffusion on social media. So this story is about an astronomer who went to South Africa and with a new powerful telescope, and in the same period he was there, a science editor wrote during an entire week a lot of different reports about the discoveries on the moon, such as those giant man bats who spend their day collecting fruits and holding conversations. And the reason why he wrote those reports is to increase the circulation of the paper, who double the copy sold in that period. And so in this case, you know, there is a presence of a clear reason why a certain person wrote these false reports, and it is easy to track back to the author and its reason. But in our new digital environment, it's really a difficult task to understand who starts the misinformation and the real reason. There are really many, from clickbaiting to many others. And this is a brand new example from 1 month ago about this picture about of refugees in Lebanon under a snowstorm, and the same picture was taken by a politician 3 days after, and the number of shares and retweets is really different, from 6 of the original picture of refugees to about 18,000 shares for the fake picture, which is in the post. It is written there. It's basically written that they are Italians who are under snowstorm, but it's not true. So that's example show you that the paradigm of news consumption and even their impact in societies is quite different from 19th centuries, because as I said before, this information can create a large-scale sharing and cross-platform cascades, and until now it's really difficult to understand which is a policy which is satisfactory to regulate from one side the social media platforms and to enable people to discuss and to talk on social media without restriction and censorships. We choose to study social media because on social media the number of people and the role in news diffusion of the social media is increasing. As you can see here, about 40% of people, or European people, get most of their news on social media or in websites. And in this graph you can see that the most common platforms where people get their news are Facebook, YouTube, and Twitter. Misinformation diffusion has been already studied and analyzed from researchers from many different research areas, such as statisticians, computational social scientists, physicists, mathematicians, and there are some key features that have been already studied, and I'll just briefly mention and then explain more deeply which are. The presence of echo chamber is one of the maybe most known feature, which is basically the formation of community which are separated from features such as the user sharings, the same consumption patterns, and the basically the way of thinking and the way of discussing about specific topics. The polarization on social networks, so the creation of really well-defined opinions about topics, and the presence of not only well-defined but even extreme opinions about topics, and the massive presence of social bots, which are mainly automatized accounts who act as credible users and manipulate the discussion. So, as you can see here, in a study of a dataset of about 70 public Facebook pages of scientific and conspiracy news, you can see that the topology of distinct communities, which are the echo chambers, is really clear. If we define the polarization as the number of likes user perform on a page of science or conspiracy with respect to the total number of likes, the communities are really well defined and are polarized on those two topics. This is another example with another study of Facebook pages of pro and anti-vaccine users, and in this case the user liking and commenting behaviors show the same pattern. And here you can see another social media, that is Twitter, and another subject, which is a discussion about a California law on vaccination. And as you can see on this network, the node size represents the influence, that is the number of times a user is retweeted, and the color represents the bot score measured with a machine learning algorithm to understand his behavior and his specific patterns. And the red nodes are bot accounts, while the blue nodes are humans, are likely to be humans actually. And as you can see here, in the core of the network there is a huge presence of both with a strong and high influence. That is a number of times the number of retweets really high. So the situation is a little bit scary on discussion on Twitter. And to talk about my specific proposal, my PhD proposal, those are the four main research questions. So I'm going to study the differential propagation between verified news and misinformation, if it exists, and if so, how they differ. So we would like to test the Levy flies, which is a motion patterns of studied in several contexts, such as for instance financial markets, and is basically a random walk. And yeah, we would like to test this motion pattern in misinformation diffusion. The second research question is about the multiplex network influence on misinformation diffusion. That is the presence of different social platforms can influence the misinformation diffusion, and how. So we would like to study the influence of different echo chambers and the cross interaction between platforms to see if, including a multiplex networks topology, the diffusion differs. And the influence of narratives, which is a really important feature on misinformation diffusion, and in particular we would like to study the influence of specific keywords in the misinformation diffusion, and which is the connection with those keywords, and the presence of both activity, how affect the misinformation diffusion network. So our preliminary results are about 2018 Italian elections, and we extracted data from Twitter about election, following several keywords, which are hashtags on Twitter, and those are the main hashtags we follow. And we extracted data from January 28 to March 19, so 2 weeks after the elections. And this is a representation given by Inside Marketing about the most used hashtag in this discussion. And we built, first of all, an indirected bipartite network. In particular, I'm building a a bipartite network of two layers, the layers of users and the other layer of hashtags. An edge between a user and an hashtag indicates that this user U uses this particular hashtag H, and we project the on the layer of user to see the communities which are formed by those users, induced by the hashtag they use during the discussion. To do that, we used a technique already applied in other researches, and is basically a measure of the similarity of the nodes, measuring the number of the common neighbors they shared. So if a user points to a specific hashtag and the same user have a strong intersection, those users are really similar. And to validate this, to project this bipartite network on one layer, we used a null model, which is a bipartite configuration model. And then we use this model to calculate and then validate with a procedure called FDR the p-values. So in this way, we don't consider all the connection, as we can see here from this example of the World Trade Web. The World Trade Web is basically the bipartite network of the countries and the goods and the products they exchange and they export. And from the naive projection, so if we use all the connection, the projection is this one. So there are basically all connection by all the countries. But if you use this this technique, the situation is really different. So we see different communities of countries which share a great number of a huge number of products, and they have similar economies somehow. The first results are obtained by difference projection on different bipartite networks. In particular, the retweet networks of non-verified and verified user. So if a non-verified user retweet a verified user, it exists a connection, an edge between them, and the information flow network of users and hashtag. So the same structure of the retweets, but with user in one layer and tweets in another, with a directed network. So there is a difference between tweets and if a user tweets a certain message or if it is retweeted. And from this network we obtain in a paper which is published, which is in archive, as a preprint and archive, we obtain really promising results. The fact that there are 4 main political communities that are extracted without a manual labeling of the politician, and as you can see here, the community are strongly polarized, because in the same the verified user of one community interacts with just non-verified users in the same communities, and vice versa. And that these communities shows non-trivial political alliances. For instance, the right-leaning communities shows 2 sub-communities. This sub-community of Forza Italia is more is closer to Partito Democratico, which is in another community, and this community of Lega is really close to Movimento 5 Stelle, which form together a government. So basically, in this paper, it is shown that by discussion on Twitter, it is possible to somehow observe the political closeness of politician without any manual labeling. So that's my preliminary result. What's next? We would like to build an hashtag projection to verify the keywords dynamics and the network topology. As I said before, we would like to test the Levy flights, motion patterns for these specific keywords diffusion, and we are extracting other Twitter datasets to apply those techniques even in other contexts. In particular, we are taking data about climate change discussion worldwide, so it's really a lot of data. Migration and vaccination policies in the Italian discussion, which are other topics, but could be really interesting to study and to analyze. And that's it. Thanks for your attention.
Thank you, Tommaso. So now we have half of the picture. Okay, it's been, I think, a very interesting and fruitful day. Tomorrow morning we will start with many other different topics, so get some rest, and let's get together again here tomorrow at 9, okay, for the second day of the PhD workshop. Thank you for being together.